All right, so we just talked about the power model. However, not all curve relationships between two variables follow a power model. In fact, there are many models. You're only responsible for two in this course, the power model and the exponential model. You've heard of exponential growth before, population growth, money growing in an account, radioactive decay. Those are all exponential growth models or exponential decay models. An exponential model between two variables has this form, y equals a times b to the x power. The distinguishing feature here is that the variable is the exponent. That's what makes it a power model, that's what makes it an exponential model, whereas power models are like polynomials. So exponential model is really easy to do. You just take your original x value versus the natural log of your y variable, or the log base 10 of your y value. Okay, so it's kind of like a power model, you just don't do the natural log of your x. And that will give you this power model. If this transformation straightens out your data, that will give you a exponential model, okay? So let's do some M&Ms. Student opened up a bag of M&Ms, dumped them out, and ate the ones that had the M on top. The idea is that each M&M has got M on one side and nothing on the other. So when you dump them out, you'd expect about half of them to have M's up. So they ate the ones that had the M's up, and they left the ones that didn't have the M's up. So then they picked up the remaining 30, because there was 30 left over. So after he ate one course, there were 30 M&Ms left over. Mixed them up, dumped them on the ground, on the table, and then ate the ones that had the M up. Kept on repeating that over and over until he got down to 0 M&Ms left over. Took 7 courses, if you will. So let's find a way to use your course to predict the number of M&Ms remaining. I got the data in my calculator. Let's first look at the original data set. Maybe we don't have to transform it. Maybe it's going to be linear. Probably not, at least not in this section. So it's curved. Looks like some kind of decay model, or it could be polynomial. Power model could work. So let's try the power model. Let's take the natural log of course and the natural log of the M&Ms. So this would be the natural log of A, column A. This would be the natural log of column B. Oops, not there. I don't want that there. Right, got to put it in the equation. Natural log of column B. So let's see what that graph looks like. Natural log of course, natural log of M&Ms. So it certainly made it more straight, but I think you can still kind of see some curvature to it. So I don't think you want these points as high as these points. These points seem like they're too high. So let's try the exponential model. It's the only two models we know. Original x versus a natural log y. So I already got the natural log y, just put in the original x's. There we go, and that just straightened that right out. So now we're good. So let's run the linear regression, the linear regression model on it, and I get an error. Argument must be in the specified domain. So first of all, I count 6 points. 1, 2, 3, 4, 5, 6. But I had 7 courses, so something's going on here. If you go down to the bottom, you're going to kind of see it here pretty easily. Why is this cell undefined? Because we tried to take the natural log of 0. So if this point is undefined, it just omits it whenever it goes to plot it. However, whenever you go to do the regression, it doesn't match up. So let's just delete that whole row. We could argue that, oh crap, I did delete all of it. Control, undo. Control, undo. All right, well, I guess I got to put these back in here again. Let's take the natural log of A and the natural log of B. Let's try this again. So I think we got the same graph. We're good. Now the linear regression should work. And it does. So 4.06 minus 0.681. So this is the natural log of the number of M&Ms predicted is equal to 4.06 minus 0.681. Oh gosh, did I remember it? Nice. Times the original course. We didn't do a transformation on the x variable. So this should simplify to an exponential model. So let's solve it. Take exponentiate both sides using a base of e. So your M&Ms predicted is equal to, let's separate this into e to the 4.06 power times e to the negative 0.681 times course. So this is just a number. We need to figure out how to handle this. I don't want e to a power with a coefficient, with course with a coefficient. I just want some base b to the course power. So here's how we're going to handle that. So e to the 4.06 is just a number. Let's find out what that number is. So e to the last answer, 57.9. Then here I'm going to write this as e to the negative 0.681 to the course power. Again, this is a property of our logs, of exponents, sorry. If you take a power of a power, what do you do with your exponents? You multiply them. I'm just kind of doing that one that I'm going backwards from the one we normally use, if you will. And this is just a number. Number of M&Ms is 57.9. This is, let's type in that number, e to the, it's my slope, I think, 0.506 to the course power. And there is our exponential model. Now, if you had this problem in pre-calc, you probably would have just not even used regression in order to find the equation. You would have just said A is your initial amount. If I'm starting with 30 M&Ms and I ate half of them, that means I would have about 60 to start with. And then every time I have another course, I'm going to reduce the number of M&Ms by half. Probably would have came up with this model just using intuition, if you will. And you can see that this is very similar. It's a little slightly different because, as you can see, you know, we had different values. They didn't get half every single time. So this is kind of the predicted best model, if you will. Okay? All right, last question of the year. Lupe is shopping for a used car and collects data on age in years and price in thousands of dollars for Ford Taurus sedans. On this page is a computer output for 3 different regression models. So we got price versus age, log price versus age, and log price versus log age. And those logs are all base 10 logs. So we got to be careful about that. We're not using natural logs here. Doesn't matter what logs you use, by the way, as long as you're consistent. Questions are on the next page. Explain how the information provided suggests that a linear model may not be appropriate for describing the relationship between age and price. Well, it's kind of a stupid question because this is not linear, because this has a pattern. So I guess, you know, we should answer it properly though. The residual plot for age versus price has a pattern. Therefore, a linear model is not appropriate. Question 2. Would an exponential model or a power model provide a better description? Use the information provided to justify your answer. So this is obviously off the board. This looks pretty straight and this looks pretty random scattered. So I'm liking this one. This is log price versus age. That's an exponential model. Age is your x, log price, that's your y. So log of your y, that's... This one here is closer to straight than the original data set, but there's still some curvature there, and I still see a pattern here. This would be the power model, and it is a no-go. So exponential model would be our go-to model. Why? Well, if x versus ln y produces a linear model, linear relationship, then an exponential model is appropriate. The graph of age versus log of price has a residual plot with no pattern. So an exponential model is, oh my gosh, I kind of worked myself into a quarter here, I'm sorry. Does that even make sense? If x versus log y produces a linear relationship, then an exponential model is appropriate. In this case, age versus log price has a residual plot with no pattern, so it's linear. And an exponential model is appropriate. I'm sorry, that's not a very good explanation. I was so excited to our last problem, and then I dropped the ball in my explanation. Whatever, something like that. Give the equation of the model you chosen to using transform variables. Okay, so we got original x versus log price, and I've got a y-intercept of 1.44 and a constant of negative 0.0907. So we got log of price. I'm using capital logs. Log of price is equal to 1.44 plus or minus 0.0907 times original age. Looks good to me. Done. Use the model to predict the price of a 5-year-old Taurus. Log of price. Oh, price hat. Ooh, that's good. That would cost us points. Be careful about that. Equals 1.44 minus 0.0907 times 5. And then to solve this for price, you just you 10 it. So my predicted price is 10 to the power of 1.44 minus 0.0907 times 5. Type that in our calculator and we're done. 10 to the 1.44 minus 0.0907 times 5 equals 9.694. 9.694. That is not $9. I think this was in thousands of dollars. So be careful about stuff like that on the AP test. $9,694. Very good.